we have been talking about the design principle used by nature, and we have seen in the past the beauty of this design and how the design makes all the difference in reactivity, in rate of the electron transfer and other aspects. Today, we will be looking at some of these very interesting aspects like fixation of nitrogen from air. If you look at the composition of air, what you find? You find that 78% is nitrogen and 20.9% is oxygen, and rest other gases like argon only 0.9%, carbon dioxides 0.03 and other gases are 0.17%. So, nitrogen is present in 78%, and can we utilize nitrogen? Indeed, nitrogen is a common compound of many important natural and synthetic compounds. Now, as you all know, nitrogen is inert. Now, how inert is this nitrogen? Now, if you look at this bond dissociation energy, it is 225 kcal per mole, it is a huge amount. So, very high bond dissociation energy. Indeed, in the laboratory we carry out reactions under nitrogen, assuming that they gives inert environment. So, it is so inert. So, we treat them like inert gas. So, looks like the activation of this dinitrogen is a difficult task. Now, let us look at the molecular orbital diagram of dinitrogen. As you can see that highest occupied molecular orbital, which is a sigma orbital, contains 2 electron, it is a bonding orbital. Now, if you calculate the bond order, it is 3 very high bond order. So, that is the reason why it is so inert. However, if one like to oxidize or reduced in any chemical reaction, what would happen? Say if we like to oxidize, then he has to remove that 1 electron from a bonding orbital, which is sigma. So, it is very difficult task. But if dinitrogen likes to be reduced, what would happen? So, electron have to go to pi star anti-bonding orbital, so which is again difficult. So, removing an electron is difficult, adding an electron is also equally difficult. So, that means oxidation and reduction looks like a difficult task. This has been reflected in some of this molecular property as shown over here. This delta HF 0 is a standard enthalpy of formation, proton affinity, electron affinity, ionization potential and HOMO-LUMO gap. If you look at the table, along with nitrogen, there are many other gas or gaseous molecular shown here like acetylene, carbon monoxide, methane, ammonia, hydrazine, all these have been compared. Now, what you see that this HOMO-LUMO gap is too high, 10.82 electron volt, that actually explains that why it is so inert. And if you look at this proton affinity, what you find that it is the lowest in the series. That means, it is extremely difficult to protonate, even with a strong acid it is impossible task. And if you look at this electron affinity, this is large negative. Ionization potential values very high positive. So, these are the indicator that why dinitrogen is so inert. So, like other factors such as molecules non-polarity, its high ionization potential and negative electron affinity determines nitrogen inertness. Now, let us look at that the most important chemical reactions, which is the conversion of nitrogen and hydrogen gives rise to ammonia. So, if you look at this, what you see that delta G is around 4 kcal per mole, that means it is a negative, that means it is thermodynamically highly favorable reactions. If this being so, then what is the problem? The problem is, although the reaction is thermodynamically favorable, but the problem lies in overcoming the kinetic barrier. You just mix it, it is impossible to get ammonia. So, the question is that how inert is this nitrogen gas? As we have just seen that nitrogen plus 3 molecule of hydrogen gives rise to 2 molecule of ammonia, which gives delta 0 large negative values. So, it is thermodynamically favorable. However, at pH 7, the reduction, the nitrogen plus 8 proton plus 6 electron giving rise to 2 NH4 plus, the E0 prime, the formal potential is only minus 280 millivolt. So, this is a feasible reactions in the biological system. This is not too negative. So, if this is the case, then what is the cause of its kinetic inertness? As you can see, these reactions, nitrogen converting to ammonia, it requires 6 electron and 6 proton in a concerted process. You have to add 6 proton and 6 electron all at a time, then and then only this nitrogen can convert to ammonia. If you cannot give 6 proton and 6 electron in a concerted way, then you end up with intermediates. And as you can see here that N2 converting to N2H2 and N2 converting to N2H5 plus. If you look at the formal potentials are very large negative value, which is impossible at the biological system. This large potential like minus 1000 to 1500 millivolt for N2 to N2H2 and for N2 to N2H5 plus this is minus 695 millivolt, which is a very large negative potential and impossible in the biological system to generate this. Now, if you look at the diagram, what you see that N2H2 and N2H4 are highly unfavorable because of delta G is large positive values and looks like it is an impossible task to go through this all this intermediate to reach ammonia. So, we see that if one can give 6 proton and 6 electron all at a time, then N2 plus H2 can give rise to ammonia. However, it is difficult if it is not all at a time, then it will go through highly unfavorable intermediates and then this nitrogen and hydrogen converting to ammonia is an impossible task. Now, how one can overcome such high energy barrier? Yes, it is possible. This energy barrier of these intermediate formations can be reduced drastically by the addition of metal. Indeed, this coordination with the metal reduces this energy barrier, and then you can see that M into H2 and M into H4, all these intermediates are highly favorable situation, and it can lead to the formation of ammonia. Indeed, biology has taken this path, so that this formation of ammonia becomes easier. We will see in details. Now, what happens in industry? So, industrial production of ammonia, which is basically nitrogen plus 3 molecule of hydrogen gives rise to 2 molecule of ammonia, which eventually converts to urea. If you look at the conditions of this conversion is iron molybdenum catalyst and more than 200 atmospheric pressure and very high temperature like around 450 degree centigrade, and this produces only the conversion rate around 15%. This is indeed the Haber-Bosch process, and this conversion is so important that they were awarded Nobel Prize, of course, in 2 different time. Haber got Nobel Prize in 1918, Bosch got Nobel Prize in 1931, improving the conditions for the formation of ammonia. This formation of ammonia, which eventually can be converted to urea, is very important for our farmers, because this urea is one of the very important fertilizers used for agriculture. So, not only this urea, indeed ammonium sulphate, nitrate and liquid ammonia, all around 80% would be nitrogenous ammonia related products, and there are 5% nitric acid, 7% nylon and other uses also there. Now, if you look at the world consumption of ammonia, you see that China is consuming a huge amount of ammonia, followed by United States, India and European countries, all farmers utilize this ammonia, and they actually produce lots of nitrogenous fertilizer for their agriculture. The heterogeneous catalyst at the heart of the industrial Haber-Bosch process for ammonia synthesis, which ranks among the largest production process with a production exceeding 10 to the power 8 tons per year of ammonia. So, you see that formation of ammonia is so important for us. However, nature has designed in such a way that there are few plants, we call it leguminous plant, they fixes aerial nitrogen very easily, and you all seen this root nodules where there is an enzyme called nitrogenase is present, which fixes aerial nitrogen to ammonia at room temperature and normal atmospheric pressure, and this is very important. So, nitrogenase is the enzyme who does all this miracle in biology. Now, the reaction is N2 plus 8 electron and 8 proton produces 2 molecule of ammonia plus hydrogen, and this reaction is happening at room temperature and normal atmospheric pressure, and this is what is happening because of nitrogenase enzyme, and we like to understand that how nature is actually fixing this aerial nitrogen so easily. So, nitrogenase enzyme that responsible for the atmospheric fixation of about 10 to the power 8 ton per year of nitrogen to ammonia necessary for the biosynthesis of nitrogenated natural compound such as amino acids and nucleic acids. You see that how important is this for our biological system. So, this is the X-ray structure of nitrogenase enzyme, and as one can see that there is huge protein chains which are wrapping around these molecules, and if I remove this protein chain, you can see that are coming, that metal cluster that are coming immediately, iron sulfur cluster over here, and you can see the structure in the chem draw I have shown over here. Then this is also similar to iron sulfur cluster, but not exactly identical. This is, we call it as a P cluster, and this is that iron molybdenum cofactor. The structure is shown over here, and we now know exactly how this cofactor actually looks like. So, this is what is the structure of iron molybdenum cofactor, and there this is the active sites where this nitrogen is converting to ammonia. Crystallographic studies spanning over 30 years have led to the current knowledge of this iron molybdenum cofactor structure in its resting state. It is, as you can see, is a cage like arrangement of one molybdenum over here and 7 iron centers, 1, 2, 3, 4, 5, 6 and 7 iron centers, and a central non exchangeable carbon single atoms in the central cavity of the cage during nitrogen reduction. This coordinatively saturated molybdenum center is saturated by 3 sulfide, 1, 2, 3, 3 sulfide and 1 nitrogen from histidine, and also a unusual bidentate homocitrate ion. You see, this is the homocitrate ion, it is coordinating in this bidentate fashion to molybdenum. In the crystal structure of the resting state, no available coordination sites for dinitrogen unit is present around the molybdenum center. One of the 7 iron center, the one most distant from the molybdenum atom of the cofactor, is tetragonally coordinated to 3 bridging sulfide group, 1, 2, 3 and 1 cysteine sulfur. The remaining 6 central iron atoms are in tetragonal coordination, 3 ligands being sulfur bridges, the 4th being the carbon atom. The 6 central iron atoms constitute 3 open iron 4 S4 phases, and as I have said that this iron molybdenum cofactor is responsible for this conversion of nitrogen to ammonia. You can see that N2 plus 8 H plus 16 magnesium ATP plus 8 electron gives rise to 2 molecule of ammonia and a hydrogen and 16 magnesium ADP plus Pi. ATP is giving the energy, huge amount of energy is required, is provided by ATP converting to ADP and giving rise to this Pi phosphate, and this reaction also helps maintaining an anhydrous atmosphere and appropriate pH at which the enzyme is most active. So, all these reactions are coupled and this is very important. So, along with reduction of nitrogen to ammonia, you see that one molecule of hydrogen also produced during this transformations. Now, this is the proposed p cluster structure. It is not exactly iron sulfur cluster, as you can see that there are two iron sulfur clusters connected with the cysteine sulfur, and this p cluster are thought to be involved in the electron storage and transfer, and presumably provide a reservoir of low potential electrons that to be used by the metal center during the reduction process. You see that this is not just like simple 1 or 2 electron reduction, this is actually, as you see earlier, that reduction of 8 electron, and which yields 2 molecule of ammonia and hydrogen. Okay. So, this is a highly reduced state and lots of energy is required, and this is why nitrogenase is so special. Now, the overall reaction, as I have discussed in my previous slide, is that nitrogen converting to ammonia and one molecule hydrogen also simultaneously being produced during this transformation with the help of huge amount of energy which is being utilized for this reduction process. So, this process requires large number of electrons, that here 8 electrons, and also huge amount of energy which is provided by the ATP. So, as one can see that this is iron protein unit which is represented as a green, and this ATP binding sites is shown here. So, ATP produces ADP plus phosphate and releases huge amount of energy which is required for this reduction process, and iron sulfur cluster in giving this electron to this p cluster, which actually store all this electron and gives to this molybdenum iron cofactor, which is actually responsible for this dinitrogen reduction to ammonia and produces also hydrogen at the same time. Now, how it gets so many electrons which is required for dinitrogen reduction? As one can see that the reduced organic which gives electron and reduces NAD plus to NADH and thereby oxidize to oxidized organic. Now, this NADH which is reduced by this way after taking the electron, then gives the electron to ferredoxin, and then this ferredoxin getting reduced, and at the same time NADH is getting oxidized to NAD plus, which then again start taking one electron from the reduced organic like this. Now, the ferredoxin which is in the reduced state then gives electron to p cluster, and p cluster get reduced, at the same time ferredoxin get oxidized. So, one get oxidized, one get reduced, and they are all coupled. So, this is the way electron is transported from reduced organic to p cluster, where it is stored, and this p cluster gives electron to iron molybdenum cofactor, and iron molybdenum cofactor get reduced, whereas p cluster gets oxidized. And this iron molybdenum cofactor, where actually the reduction of dinitrogen is taking place, it requires large number of electron and protons, and this iron molybdenum cofactor gives this electron, and this nitrogen is produced to ammonia in this way. Now, this is what is the schematic representation of nitrogenase enzyme. As you can see that this iron protein, which molecular weight is around 65,000 Dalton, which is shown in a square block, and this supplies electron to the p cluster, which actually indeed store all this electron, and the energy actually 16 ATP unit per dinitrogen is required, and this huge energy is provided by the ATP, and ATP converted to ADP plus phosphate and releases huge amount of energy which is required for this reduction process. And this p cluster stores these electrons and gives electron to iron molybdenum cofactor and for its reduction of dinitrogen to ammonia. As I have already informed that during this process also hydrogen is being produced. It is not known clearly that how hydrogen is also getting produced during this process. What is the use of that? Possibly this hydrogen also maintain the very reducing environment which is required for such 6 proton and 6 electron reduction process. So, overall reactions is nitrogen getting converted to ammonia and hydrogen at the cost of huge amount of energy and electrons. Now, proposed nitrogen reduction pathway, so it is still not very clear how actually dinitrogen is getting reduced in iron molybdenum cofactor. There are controversies, I am not going to enter into that. However, a schematic presentation is shown over here. So, metal binds dinitrogen and this with 2 proton it forms diazine. As you can see that this has formed NH and this diazine after addition of one more proton converts to hydrazido NH2. This hydrazido after giving one more proton is forming hydrazine, and this hydrazine releases one molecule of ammonia in presence of one proton, and this intermediate which is being formed releases another molecule of ammonia with the help of one more proton. So, you see that there are 6 proton 2, 3, 4, 5 and 6 protons is involved to produce 2 molecule of ammonia. There is another way also this reduction is also possible. This first form diazinido intermediate like this, where only one terminal nitrogen getting protonated to convert to NH2 diazinido formation, and which then releases one molecule of ammonia with the help of one proton, and this nitrido intermediate produce imido in presence of one more proton converting N to NH, and this imido produce MNH2 in presence of one more proton here, which eventually releases one more ammonia after addition of one more proton. As you can see, during this reduction process 2 molecule of ammonia is being released, and this require 6 proton and 6 electron for just dinitrogen reduction only. Okay. It is interesting to see that how this metal indeed stabilize those intermediate, and this is actually happening as I have shown in my earlier slides, that these highly unstable intermediates can be stabilized upon coordination with the metal. So, metal indeed stabilize those high energy intermediate, and this is what is happening. In order to prove this principle, people have made various attempts in laboratory and they try to stabilize the intermediates which is otherwise impossible to understand. So, for example, this N2 converting to N2H2 with the help of 2 proton and 2 electron. Now, as I have discussed, this is an extremely unstable intermediate in the free state. Delta HF is 212 kilojoule mole inverse in the free state. Now, can this intermediate be stabilized in presence of metal? Indeed, this is the question arises by what means it is stabilized in nature at the metal center of nitrogenase in order to avoid high energy barrier in the course of nitrogen reduction. This was indeed possible to trap this very unstable intermediate with the help of metal center. As you can see, this N2H2 is being trapped between 2 iron center here, and this is pentadentate ligand which is coordinated to iron, and then the 6th position this iron nitrogen bond is there which actually trap this very unstable N2H2 intermediate, and this intermediate also further stabilized by these NH sulfur hydrogen bonds. The excess structure of this molecule was determined by Selman et al. Long back in 1989, and one can see that this N2H2 is present over here, this NN distance is 1.300 angstrom, and this proton has also been located in the X-ray structure which confirms the presence of N2H2 between these 2 iron centers. These results show that this N2 to N2H2 conversion, the most difficult step of nitrogen fixation, should be facilitated and possibly even become exoenergetic. Today, you have seen clearly why the design is so important. The conversion of nitrogen to ammonia, which is an extremely difficult task, can so easily be achieved in biology even at room temperature and normal atmospheric pressure by nitrogenase enzyme. So far, the best known industrial synthesis of ammonia, which is indeed the source of many fertilizers used by our farmer, requires very drastic conditions such as high temperature and pressure. If we understand the design principles of nitrogenase correctly, we can then simply implement such knowledge in the laboratory for various useful applications. The nitrogen that is present in air in large quantities can then be converted to ammonia so easily, and thus would reduce drastically the cost of all nitrogenous fertilizers used by our farmers. It would solve all the food problems in the earth then. We are indeed eagerly waiting for that day to come. Thank you.